Math time!
Hello everyone, this is Math 504 Advanced Calculus, and this time we're going to talk about some problems or solve problems about integrals. And to start with, let's have the techniques of integration. So we have here our problem. We are asked to evaluate each integral by using a substitution to reduce it to standard form. And we are asked for problem number 8. So we have here our problem number 8, the integral of 4 dx all over by 1 plus the quantity square of 2x plus 1. So to solve this one, we have the first thing that you're going to do is to let or set u be equal to 2x plus 1. So that's why you would have du is equal to 2 dx. By substituting, you have there, substitute u and du into our integral. So we have there the integral of 4 du all over 1 plus u squared. Alright? So right there, we may now proceed with the integral in the form of the dx over 1 plus x squared, which is our standard integral. So, the antiderivative of 1 over 1 plus x squared is arctan of x plus c. Okay? So, therefore, our integral, we would have then that our integral for dx over 1 plus the quantity square of 2x plus 1 is just equal to 4 arctan u plus c. So what shall we do with this one? We're going now to substitute back our u, which is our 2x plus 1. Okay, so right there, so our final answer would gonna be 4 arctan of 2x plus 1 plus c. So again, this is now our final answer for the problems on problem number 8 rather. Moving on, let's now proceed with the trigonometric integrals. Okay. And for the trigonometric integrals, we're asked to evaluate this problem number 3. So from our integral from 0 to 5, you have the square root of 1 minus sine squared t dt. So to solve, you have use the trigonometric identity. Remember our trigonometric identity that says cosine squared t plus sine squared t is just equal to 1. So as we are going to look for the sine squared t, you would have there 1 minus cosine squared t. So we're going to make use of this one as we're going to solve our problem. So to solve, you have to substitute. From there, you have the integral of 0 to pi square root of 1 minus sine squared t dt is equal to, as we substitute the value of our 1 minus sine squared t, so you have there cosine squared t. So as we are going to simplify it out, take the square root and the square, that's why you have it here, the integral of 0 to pi cos t dt. So you're now going to integrate cos t. So with respect to t, now as we integrate that one, we have there sine t 0 to pi. And of course, as we evaluate sine pi and sine 0, you have therefore, okay, can we have this one? So therefore, we have sine pi minus sine 0. So take note that sine pi is equal to 0 and sine 0 is equal to 0. So therefore, our final answer would gonna be 0. So of course, 0 minus 0 is equal to 0. So right there, our integral from 0 to pi, the square root of 1 minus sine squared t dt is just equal to 0. Is that clear now? Moving on to our next problem with the problem involving volumes of a cylindrical shells. Okay, so we are asked to use the shell method to find the volume of the solids generated by revolving the regions bounded by the curves and lines about the x-axis. Okay, so our problem here is x is equal to 2y minus y squared, where x is equal to 0. Okay, so we have here our steps to follow as we are going to look for as we determine, the solution. So our solution would gonna be, first, we have to determine the limits of integration. Since the region is bounded by x is equal to 2y minus y square and x is equal to 0, so we can find the intersection of these curves. So we have 2y minus y square is equal to 0. So you have to y is equal, the quantity of 2 minus y is equal to 0. So to solve for y, you have y is equal to 0, and the other one is 2y minus, 2 minus y. We have this one. Okay. Okay, so 2y minus y is equal to 0, so therefore y is equal to 2. So since the limit of integration will be from 0 to 2, we can then determine the radius of each shell. So the radius of each shell is the distance from the shell to the axis of rotation, which is simply the value of x. Okay, so in this case, we have radius is x. Now moving on, so to finally get the answer of this problem, okay, so we are going to determine also the height of each shell. The height of each shell is the difference between the upper and the lower functions. In this case, it's x is equal to 2y minus y square minus 0 is equal to 2y minus y square. Alright, so next step is we're going to write the integral for the volume using the shell method. So here is our shell method. Volume is equal to 2 pi, the integral of a to b, x times h of y dy. So wherein you have here the a and b are the limits of integration. Y of y, h of y is the height of each shell. So the integral becomes v is equal to 2 pi, the integral of 0 to 2, the quantity of 2y minus y square times the quantity of 2y minus y square dy. So as we simplify it out, you have it therefore, they're just the same. Alright, so moving on, you have 2 pi, the integral of 0 to 2 rather. As we simplify distributive property, you have 4y squared minus 2y cubed minus 2y cubed plus y to the 4th dy. So simplify it out. We could have then 2 pi with the integral of 0 to 2, the quantity of 4y squared minus 4y cubed plus y to the 4th dy. Okay. So what shall we do with that one? Let's now evaluate the integral. So as we are going to evaluate, you have then 2 pi times the quantity from 0 to 2, 4 over 3 y cubed minus 4 over 4 y to the 4th plus 1 over 5 y to the 5th. That is integrating each term separately. So plugging the limits of the integration, so therefore you would have there this solution. Okay, there you go. Okay, so moving on, you could have then 2 pi times 32 over 3 minus 16 over 4 plus 32 over 5 minus 0 plus 0. A total of 160 minus 60 plus 96 all over by 15. As we simplify it out, that is 2 pi times 196 over 15. So what does it mean? Okay, in this case, you have then therefore that the volume is equal to 392 pi over 15. So again, the volume, the solid generated by the revolving the region about the x-axis is 392 pi over 15 cubic units. Okay, so I think that would be all. This is Math 504 Advanced Calculus. This is once again Anisito R. Puertes Jr. Maed 1 Math.